Okay, and let me recall what we did last time. We considered a surface, but rather simple surface, the product of two curves. And then we had the Picard group of this surface. And inside we had the subgroup of decomposable invertible sheaves. Like this. And let's call this quotient group the reduced Picard group. Pick bar or overline. Okay, so now say by unit formula, if some invertible sheaf L in the Picard group of our surface is decomposable, that is, L is the pullback from C of certain line bundle on C, tensor the pullback on S, certain line bundle on S. So if this is so, then the Euler characteristic of our L is the product of Euler characteristic of LC times the Euler characteristic of LS. And we introduce the for indecomposable L, for arbitrary L, we introduce so-called defect n of L is the difference, the Euler characteristic of well, I will recall momentarily what I mean by this, of L times the Euler characteristic for S of L minus the Euler characteristic of L itself, where Chi of L is the Euler characteristic of any fiber C times S with coefficients in L restricted to this fiber, and similarly Euler characteristic along the other factor is the Euler characteristic of restriction. Oops, sorry. C times S with coefficients in the line bundle restricted to any vertical fiber like this. Okay. So what else did we define last time? We defined the degrees. Deg C of L is the Euler characteristic of this restriction plus G minus 1. G of C, the genus of the curve C minus 1. Similarly, the degree along S is the Euler characteristic along S plus the genus of S minus 1. And those are degrees of L restricted to fibers, I mean to vertical fibers or to horizontal fibers. Okay, so these were definitions from the last time, and now the theorem we're going to prove. is that first of all, this defect N of L is well defined on the quotient group, modulo decomposable invertible sheaves. Second, it is always non-negative. And third, it is zero or only for decomposable line bundles. If N of L is zero, then L is decomposable. Okay, so in other words, it defines some positive definite form, and then next theorem will prove that this form is quadratic. Okay. So here is the argument. So first we have to prove that our defect does not depend on if we tensor by some line bundle lifted from C or from S, then the defect stays the same. Okay, so we have to check that the defect of L stays the same if we twist our L by some vertical or horizontal divisor. Well, let's consider only horizontal divisors. It doesn't matter. Like this, for any point C, because any line bundle comes from a divisor, as we argued a few months ago, and any divisor decomposes into a linear combination of points. So we can add a few points or subtract a few points, and there we are. So let's consider short exact sequence. Here we restrict our line bundle to the horizontal divisor like this, and then we obtain equation for Euler characteristics. So the Euler characteristic of L is the Euler characteristic of L twisted. Plus the Euler characteristic of this horizontal fiber, but this is nothing but the.
Можно спросить?
Yeah.
L от минус C умножить на S, это сечение или это твистованный пучок?
It's a twist. Yeah, it's a twist.
Спасибо.
To twist by a divisor. This is a horizontal divisor. We twist our invertible sheaf by O of negative C times S. Okay, so we get this, and what we know also, we also know that the Euler characteristic along the vertical fibers stays the same. But you see, when you restrict to the vertical fiber, what happens? You just twist by one point, this very point C. Okay, so the Euler characteristic just drops by one. Okay, and finally, if we restrict to the horizontal fiber, then nothing changes. Yeah, because it does not depend on the fiber, and for most fibers, nothing changes at all. Oops, sorry.
Почему добавляется точка С, а не минус С?
Well, just I don't know what to say. You see what's written. You have L somehow twisted by negative C times S. So if you add C plus S, you get your L back. So when you add at one point, you get positive L characteristic plus 1. Okay. So we proved the first part. The fact that the defect that does not change if we twist by horizontal or vertical divisor. Okay, so now I have to prove this positivity, part B. And to this end, by what we have just proved in part A, we are free to change our L, twisting it by horizontal or vertical fibers, and this will be very instrumental. So we twist L to obtain some L prime, such that, well, by adding horizontal or vertical divisors, so that, first of all, the degree along C of this twisted line bundle is somewhat critical, the genus -1, and moreover, the global section of some fiber with coefficients in the twisted bundle is 0 for some point S in another curve. Okay, so how are we going to obtain this? Well, the first condition, this. The first condition is easy. Just twist by a divisor of required degree. Okay. You twist by 1 point, the degree grows by 1, or untwist, the degree goes down by 1. So you can obtain this degree G of C minus 1, and that's fine. But now the second requirement is more subtle. But what I need is that for degree equals G of C minus 1 invertible sheaf L on C, the global sections with coefficients in this sheaf are 0 for, so to say, general L. And well, we know that all those L run through the Picard variety of degree G of C minus 1.
Да, раньше же у нас пучок L был на произведение Декарта, он C на D.
Okay, you're absolutely right. Sorry. Thank you for a good idea. Say M. Okay, and this. Oh, sorry. One more. Yeah. So this M will be L restricted to C times S. There's big C and small s. Okay, so when I say general M, that's what I mean. We have this algebraic variety, abelian variety, or torsor or this abelian variety, and for an open subset, the global sections are vanished, and that's what I can achieve for the second part. So let me explain this. Certainly, this condition is open. So I have, in fact, I have to find just one invertible sheaf M with this property. So, given any M, we construct well, maybe M prime as M like C1 minus C2. Okay, maybe this does not suffice. Maybe then we go to M second. This is M prime of C1 prime minus C2 prime, and so on until we succeed. So what I what I claim is that if the global sections of C with coefficients in M are not zero, then there exist 2 points C1 and C2 such that the global sections with coefficients in this twisted M well, the dimension of global sections is smaller than the dimension of global sections of the original invertible sheaf M. Okay, so then eventually I can make this dimension 0. Okay, so how do I do this? Well, I consider this space of global sections with coefficients in M, and it can happen that all of them vanish at some point. Yeah, then this point is called a base point. So there are certain base points C in our curve, such that any global section vanishes at this point. Gamma restricted to C is 0. Okay, but if our invertible sheaf is sufficiently positive, then there are no base points. For degree G minus 1, in principle, there might be some base points, but there are finitely many. So the general point is not a base point. So choose C1, not a base point. Or sorry, so maybe C2, sorry, C2. C2, not a base point. And this means that the that the dimension of global sections of M of negative C2 is the dimension of global sections of C and M minus 1. Okay, so vanishing at this not base point C2 does impose condition on global sections of M. Fine, but the Euler characteristic of M of minus C2 is the Euler characteristic of M of M minus 1. So it means that the dimension of the first cohomology of M, well, of C with coefficients in M is the same as the dimension of first cohomology of C with coefficients in M of negative C2. Okay, and
нулевые когомологии почему?
yeah, so the dimension of the zeroth cohomology dropped by 1, but the dimension of the first cohomology stayed the same. Okay.
А почему они остаются одинаковыми, нулевые когомологии?
No, the dimension of zeroth cohomology, global sections, dropped by 1. Here, the third line from the bottom, right? And algebraic also dropped by 1 because degree dropped by 1. So the first cohomology,
Понятно, спасибо.
the first cohomology dimension stays the same, but by self duality, this dimension, well, the first cohomology of C with coefficients in M is dual to the zeroth cohomology, to the global sections of C with coefficients in M dual tensor, the canonical class, and the same for C2. Okay. So these global sections are of the same dimension, and now we choose some base point, some not base point for this guy, for the second guy. So choose C1, not a base point for M of C2, then dual tensor, the canonical class. And then it implies that the dimension of global sections with coefficients in this guy. Sorry. Oh, sorry. Global sections of the curve with coefficients in this guy minus C1 tensor omega C is dimension of global sections of C with coefficients in M2 C2 tensor omega C minus 1. Okay, so then applying, and again, you have the equality for Euler characteristics and for first cohomology, and then you can apply the third duality once again. So, well, let's say unwinding the above argument with shared duality, we arrive at the fact that dimension of global sections of M C1 minus C2 is the dimension of global sections of our original line bundle minus 1. So that's what we wanted. Okay.
А зачем мы вводили пучок М с двумя штрихами вверху?
Here, because we wanted, if you remember what we wanted to achieve, the vanishing of global sections, right? But it could happen that we started with our initial sheaf M, L restricted to the fiber, who had a lot of global sections, like 5-dimensional space of global sections. And then we start working on this sheaf. Yeah, we reduced by C1 minus C2, and we make sure that the dimension of global sections drops by 1, so it becomes 4, but it's still big. So we work on it more. We twist by C1 prime minus C2 prime, and dimension drops again, becomes 3, and so on until it becomes 0. Okay, that's how it works.
Can I ask?
Yes, certainly. Yeah.
And the argument on Euler characteristics that is drops by 1 follows from exact sequence. Yes.
The Euler heuristic drops by 1 just because the Euler heuristic is always degree plus 1 minus g, right? So as long as degree drops by 1, the Euler heuristic also drops by 1. That's immediate. There's nothing to prove.
Okay, and yeah, and am I right that your argument is very similar to the argument we needed to perform in our homework on this topic?
The only problem is with my Alzheimer, so I forgot which homework did you have on this topic?
In the beginning of March.
Maybe, yeah. It was a long time ago, so I forgot everything. Sorry.
Okay, and am I right that if we have a sheaf of with many global sections, then if we twist it by G points, effective divisor, then its global sections will be empty.
And what is G? Your G genus or what? Or
yes, G is a genus of a curve.
But it depends on degree. So each time you subtract 1 point, if its point is general enough, if it's not a base point, then the dimension of global sections drops exactly by 1. So you only have to make sure that you don't choose base points by bad luck. If you don't, then dimension necessarily drops by 1.
If the degree of L is G.
Oh, then certainly each time you subtract a point, the degree drops by 1, so eventually it becomes 0, yes.
And G minus 1, if we twist by the divisor of degree G minus 1, then the resulting sheaf will have only constant sections.
Yes, yes.
Okay.
Okay, so where were we? We have to prove the last point, or well, not the last, the next point. That so next claim. Well, let me remind that where are we? We're still trying to prove this positivity. You see, we didn't yet prove point B. We're in the middle of proving B. Okay, and so far we only found some nice representative. We proved A, so that this defect does not depend on twisting by vertical or horizontal divisors. So we're free to twist as we please, and we twisted so that the degree is critical, and the sections on some fiber, and it means on general fiber, vanish, and the first cohomology vanish as well, because you see by the Riemann-Roch formula, the Euler characteristic here is 0. So both zeroth and first cohomology vanish on general fiber. And that's essentially what I want to claim next. So I claim that for this particular representative, the higher direct images for projection onto S, they are 0 unless I is 1. So once again, we know this statement for a general fiber, and now I make this claim for the sheaf on the base of projection. Yeah. So if I equals 1, this sheaf is a torsion sheaf on S, and well, also, well, that's fine, and also the first, well, the ith cohomology of our surface with coefficients in L prime also vanish unless I equals 1, and the first cohomology with coefficients in L prime is just the global sections of S with coefficient in this first direct image of L prime. Okay, so we'll prove this claim momentarily, but first let me note that it implies B, the point B, this positivity. That is the defect of L equals defect of L prime, and is non-negative. Well, just because you see the Euler characteristic, well, this was equal to the Euler characteristic along C of L prime times the Euler characteristic along S of L prime minus the Euler characteristic of L prime, and the Euler characteristic along C is 0, right? Because the degree was G minus 1, so Euler characteristic is 0. So this first summand is 0, and we get that the whole thing is just negative Euler characteristic of L prime, but we know that L prime only has first cohomology. Okay, so this thing is just the dimension of the first cohomology with coefficient in L prime, and as any dimension, it is non-negative.
Почему дефекты одинаковые у штриховной или?
This was part A. We proved this in part A. We started our proof with this assertion, right? Shall I go back? Let me go back. Here is part A, that the defect is well defined, so it does not change when I twist by vertical or horizontal divisors. Okay, so also maybe before we start proving this claim, let me remark that if n of L prime is 0, then it means that the cohomology, well, according to this claim, the first cohomology of our surface with coefficients in L prime must be 0. Yeah, it's 0-dimensional space, and then this means that we proved that the first, well, claim in this claim, it is claimed that the first cohomology is global sections of some torsion sheaf. So if global sections of torsion sheaf is 0, this means that the torsion sheaf itself is 0, right? So it means that the first cohomology, the first direct image of L prime.
Мы же должны проверять на ростках равенство нулю пучка, а не на сечение. Или почему достаточно?
The torsion sheaf on a curve. So it's direct sum of skyscrapers. And if the global sections of direct sum of skyscrapers vanishes, then it vanishes itself. And in this claim, we also claimed that this means that all the higher direct images vanish. Okay, so then we'll use it to prove the strict positivity. But first, let's prove the claim. So the claim, once again, says that only first cohomology exists. Everything else vanishes. So we know that we know that the Euler characteristic of any fiber, well, of some fiber is, well, sorry, Euler characteristic of any fiber is 0, just because the degree was equal to G minus 1. And we know that there are no global sections, so there is no first cohomology either, and no higher cohomology at all. So all cohomology whatsoever of this vanishes.
I'm sorry, but why Euler characteristic is 0 if degree is G minus 1?
That's by Riemann-Roch theorem.
H0. H0 minus H1.
Yes. I mean,
I see.
Characteristic is degree plus 1 minus G. And here you get G minus 1 plus y minus G is 0. Okay, so there is no zeroth cohomology, no first cohomology, no cohomology whatsoever. And then it means that there is some neighborhood sorry, of S. All those higher direct images vanish. Okay, but the zero, the direct image, is just the direct image itself, is torsion free, and hence it vanishes absolutely. Yeah, it vanishes on some open subset, so it vanishes everywhere. Yes. So the first direct image is torsion, as we claimed, because it vanishes on this open subset U. And the higher direct images vanish just because they vanish on any fiber. For any fiber. Okay, so there we are, and if you remember what we're proving, we proved the first part, that the higher direct images only exist in degree 1, and in degree 1 we get a torsion sheaf on the curve S. Now we have to compute the global cohomology, and well, this is some very general claim. Maybe everybody knows or somebody knows. So it's like we have C times S. We project it to S, and we project it to the point. And there is this composition. Well, maybe I should call it pi, whatever. And we know that the cohomology of C times S with coefficients in anything at all is the derived functor of the composition pi composed with per S, and then this is the composition of two derived functors pi composition with per S derived functor. Okay, and then this implies that there is some Leray spectral sequence with the second page some cohomology of S with coefficients in the higher direct images of something. So this is E2 PQ that converges to the cohomology in degree P plus Q of C times S with coefficients in something. And then it immediately implies what we need about global cohomology. But I wonder, I don't know, if everybody is fine with spectral sequences, or we need some down-to-earth argument, or what? So can somebody say something? Is it okay as argued, or shall I give an elementary argument without mentioning spectral sequences?
Could you give an elementary argument?
Okay, let's.
Сейчас я немножко запутался. Вот как вот, например, вот из этого утверждения, допустим, мы знаем вот эту спектральную последовательность, эти тоже следует утверждение нашей. Какое мы утверждение сейчас хотим из этого?
So we are proving this global claim. So we proved this about higher direct images, and now I want to prove the statement about cohomology. But I claim that cohomology of the surface C times S is more or less cohomology of the base S with coefficients in these sheaves that we already took care of. And since there is only one direct image, namely the first direct image, then this spectral sequence that I mentioned degenerates at E2, and there is just one term, and it is equal to desired cohomology. So this equality here just immediately follows from the spectral sequence.
Спасибо.
Welcome. But I'm supposed to give an elementary account. Well, just by definition of cohomology. So take the how is it called? Discontinuous sections of Flaby resolution. L goes to this discontinuous sections of L like this on our surface, and then we can compute the higher direct images using these resolutions. So projection S of ds of L is again a Flaby complex on S, computing the higher direct images. Okay, and we know by what we just proved by the first part that we proved, we know that this complex of Flaby sheaves, yes, L prime, has only the first cohomology, and this sheaf is torsion. And hence Flaby as well. Okay, and now if we want to compute the desired global cohomology, then what do we see? That it can be also computed by the same resolution. So we take global sections of this Flaby resolution. Okay.
How L prime
yes.
and L, why L prime, not L?
But I just thought that I always work with L prime. Maybe I forgot sometimes to put prime, but at least I meant to always use L prime, the special representative of good degree and
for example, when you choose Flaby resolution
so here,
of L,
it's L prime. Sorry, yeah, everywhere must be L prime. Okay, so Okay, but we can also say that this is the ith cohomology of global sections of S with coefficients in the direct image of this Flaby resolution. Okay, so well, the last claim, well, implying the second part, is as follows. So let's have a complex of sheaves. That are Flaby or more general acyclic. Acyclic means no higher cohomology. Okay, and we wanna compute the cohomology with, how to say, the cohomology with coefficients in well, say H I is the ith sheaf cohomology of this complex. Okay, then the, so to say, hypercohomology, the global cohomology, the cohomology of global sections of this complex whatever S, but this complex is just the global sections of cohomology of this complex.
А разве это не по определению пучка к гомологии вот такой тоже?
Sort of, yeah. Well, maybe we once already used this fact that you can compute cohomology using arbitrary acyclic resolution. Yeah, it's defined by some particular resolutions, say discrete discontinuous sections resolution, but it doesn't matter. You can take any acyclic resolution. So you see the taking cohomology and the global, taking, how to say, sheaf cohomology and the global sections are well, they commute. You can do it first in this order or then in the opposite order. And the proof is immediate. You just split everything into Schrödinger sequences. So you have cycles or co-cycles, co-boundaries. Like 0 to the sheaf of cycles, to f I to the sheaf of boundaries or co-boundaries, I plus 1 to 0, and also 0 to co-boundaries to cycles to cohomology, like this, and just by induction in I, all those sheaves are acyclic. Once again, the higher cohomology are 0. And then the global sections applied to all those sequences give exact sequences. Okay, so those local coboundaries and cocycles go to global coboundaries and cocycles. Okay, so finally we are done with all the abstract nonsense, and this was needed to prove a lot. The claim, what was this claim? Here it was, page 4. So finally proved this this thing, right? That we only have the first cohomology, and this first cohomology is the global sections of the base curve S with coefficients in the skyscraper sheaf. That is the first direct image under projection to S. Okay, maybe I should call this projection to S. Fine. And here too. So there we are. In particular, the part B is proved. Here is part B, that our defect form is never negative, but now we want to prove that it's positive. So if it is 0, then our invertible sheaf splits as a tensor product of two lifted from the factors. Okay, so that's what remains, and we already know that if our defect form is 0, then our sheaf L prime is to say very acyclic. Yeah, it's higher direct image to the base curve S vanishes absolutely in all degrees. The zeros, first, second, and so on, all direct images vanish. Okay, so now we can continue from here on. So we know that all the higher direct images of projection to S L prime are absolutely 0, and we want to prove that L is decomposable. Well, we choose a point in our fiber and consider a short exact sequence. L prime goes to L prime twisted by this fiber, goes to L prime twisted, restricted to this very fiber. Okay, and now recall that L prime, well, you don't have to recall much, it's written here, but L prime is absolutely acyclic. So the long exact sequence of higher direct images implies that the direct image, projection to S direct image of L prime twisted by S maps isomorphically onto the projection of L prime twisted by this divisor restricted to this divisor, this fiber. But note that this fiber projects onto S isomorphically, certainly, right? So this projection does nothing. This projection is just L prime, well, twisted, and then restricted to the fiber. And they are isomorphic once again. And in particular, this is invertible. There's some invertible sheaf on S. So let's call it M. And now we know that this M is isomorphic to the direct image. Well, let's invert this isomorphism. Like this. And now the push forward is adjoint to the pullback. Namely, push forward is the right adjoint to the pullback. And so it implies that there is a morphism, the pullback of M goes to L prime twisted by C times S by adjointness. Okay. And well, downstairs on the curve S, this map was an isomorphism, but certainly it does not mean that the map upstairs on the surface C times S is an isomorphism. It only means that this map is an embedding. So it's injective, since M and L prime twisted have no torsion. Okay, I mean, if it had a kernel, this kernel must have been a torsion sheaf, but those are just line bundles, invertible sheaves, no torsion. Okay. So,
but what you derived from by adjointness?
The existence of this morphism on the surface. Yeah, from existence of the morphism on the base curve S, I derive the existence of this morphism on the surface. Yeah.
Ядро должно быть кручением.
Pardon me?
Pardon me? Ядро должно быть кручением.
Because well, maybe I shouldn't say it like this. How should I say this? Well, so this morphism certainly is not zero, because the morphism downstairs on the base is not zero, and the non-zero morphism from an invertible sheaf can be only an embedding. It's an invertible sheaf, so if the morphism from it is non-zero, then no choice. Okay.
Почему ядра не должно быть? Я не совсем.
Because it's an invertible sheaf, and multiplying it by functions from any section locally, you can obtain any other section. And if some section goes to zero, then everything else will also go to zero.
Спасибо.
Yeah, it's like sheaf O itself. Yeah, locally, it looks like structure sheaf.
Yeah. Хорошо, спасибо.
Okay, welcome. Fine. So we obtain an embedding, and we know that what do we know about this embedding? That when I restrict it to our fiber, so well, let me call it so I know that when I restrict A to this fiber, we started with E times S. Then it's just an isomorphism from M to L prime of C times S restricted to C times S. Okay. So so I well, let's consider L prime of C times S restricted to C times S modulo A of M. Okay, and this is some sorry, not restricted. Sorry. Sorry, A of once again, we had an embedding like this, A from the pullback of M to this guy. So we consider this guy L prime of C times S modulo the pullback of M, like this. So it has it is a sheaf on our surface. S with support Z, some closed subset in our surface, and we know that the intersection of Z with this particular fiber is empty, right? Because the restriction of A onto this fiber was an isomorphism. And this implies that the projection of Z onto C is just finitely many points. Okay, because it's a closed subvariety, that is not everything. It does not contain this particular point C. So it must be finitely many points. Fine. But then it means that that our sheaf L prime of C times S is the pullback of M twisted by the sum of Ci times S. Okay, and we are done. because well, this is decomposable. Okay. So we proved this big theorem. Congratulations. And now let's at least formulate the next theorem, the quadratic form. So the defect, well, function n of L is quadratic. And what does it mean? It means that let's define the corresponding bilinear form. Sorry. So we take n of the tensor product minus n of L minus n of M minus n of the trivial sheaf, structure sheaf of this surface. And then this is bilinear, or I don't know, it means that L with M1 tensor M2 equals the pairing of L with M1 plus the pairing of L with M2. And also, if I take L1 tensor L2 and pair it with M, I get the pairing of L1 with M plus the pairing of L2 with M. Well, and also the initial degree function is just 1/2 of pairing L with itself. Okay, this is our next theorem, and somehow it is a corollary of Riemann-Roch theorem for surfaces. I mean, for the surface C times S. And next week, hopefully, we'll prove at least some form of Riemann-Roch theorem for surfaces, but we will give some elementary proof of this theorem before the general Riemann-Roch theorem. So let's start. We have 5 minutes. So let's start. And the first part is that our L is equivalent modulo decomposable line bundles to the line bundle associated to divisor that is the sum of smooth divisors. The i's are all smooth curves in this surface and are all disjoint. Okay. So let's prove this. This is a corollary of Bertini theorem. So let's consider the following divisor D. There's just one fiber, one horizontal fiber, plus some vertical fiber. Okay. Then O of D is ample. That means that O of ND is very ample for big enough n. And this means in turn that the line bundle O and D defines a projective embedding of our surface into some big, into some big projective space, namely projectivization of the global sections of this line bundle dual. Okay, so we discussed some Kodaira criterion where it happens, and in particular for curve, it takes some very explicit form. Namely, it suffices that the degree of your divisor is big enough, like bigger than twice genus of your curve. Yeah, well, and here we are. So we know that O the S of n times S small is very ample, and OC of n times small c is also very ample, and hence their tensor product is also very ample. Okay, so this we know, and there we are. There we are because say general section of O c times S of ND is the hyperplane. Well, maybe a hyperplane. A hyperplane section of c times S in this projective embedding so it is smooth by the Bertini theorem. So it is the disjoint union of smooth components And that is what we wanted to prove, right? That well, just this. Okay, so that's it, and thank you for today. Any questions?
Для чего нам понадобится вот эта квадратичная форма, которую мы сейчас будем строить?
Well, this positivity is the so-called Castelnuovo-Severi inequality, and then we will apply it to, well, it has many applications, but we will apply it to the well, under the Riemann hypothesis for curves over finite fields. We will apply it to some particular, well, we'll have some curve over finite field. We'll have inside its square, we will have the diagonal, that is the graph of identity morphism, and also the graph of Frobenius morphism. And we'll take the corresponding line bundles, O of first divisor and O of second divisor, and we will take this pairing for these two line bundles, and the positivity will imply the Castelnuovo-Severi inequality that will imply Riemann hypothesis for the number of points on the curve over finite fields.
Спасибо.
Welcome. Hopefully we'll do this just next week.
Кстати, сейчас уже вышла какая-то новость, что YouTube не заблокирует.
Pardon me? Again?
YouTube не заблокирует.
Не заблокирует. Just super. Fine, thank you very much. Though I don't believe it will last long, but at least for some time. Thank you very much, Graham. Great news. Okay, so if there are no more good news, let's stop now. So I'm saving the draft and stopping the recording.